Okay. Thank you, Antrix, for the introduction. And usually I start talks with I'm happy to be here, but looking at the audience and seeing everyone there, I wish I were there. So hopefully next year I'll be happy to be there. As Antrix said, I'm Yuval, but I will start now with a slightly longer introduction about myself, so you know a bit more. Those of you who've seen me, probably you can see me on the screen now, know that I'm an aging geek. I look like one, I behave like one, that's me. But I have not always been an aging geek. So in the 70s, I was young. I was still geek, and the Israeli school uniform, military style school uniform really helped accent this appearance. But while I was young, for those who don't believe it. And when I was young, I had a dream. My dream was to be a scientist. And to be a scientist, I learned, or I read a lot, like every young boy, about the scientists of yore. And I read about Isaac Newton and his apple. And Antoine Lavoisier, the discovery of oxygen. And Marie Curie, discovery of radioactivity and the early demise through this discovery. Anthony van Leeuwenhoek with the microscope. Gregory Mendel and his bees. And Rosalind Franklin and the DNA. Actually, this is a lie, because when I was young, no one talked about Rosalind Franklin and the DNA, but we only later became aware of that. But there was one scientist that I admired the most, and that scientist is Luigi Galvani. And there is really nothing to not like about him. He channeled electricity from lightning through dissected frogs. That's amazing. That's the real science. I don't know how to describe it. It's mostly inventive thing. I wish I could have done that, although I get a bit queasy when I see dissected frogs, so it's not the best science for me. Anyway, in his time, people continued this research and dissected other animals and also criminals. And this really gave rise to other stories, including Frankenstein is based on Luigi Galvani. And that makes him really famous. But he lived at the same time as Alessandro Volta, and somehow everyone knows about Volta. And about Galvani, people know about Galvani only from visiting the hardware store. And I don't have a real answer to the question why that's the case. But one possible solution is that Galvani was very religious. And there's no problem being religious. We can be religious, but it caused him to ignore evidence. And he believed that electricity that moved animals is different than the electricity that comes from battery, because God couldn't create God created animals, and we cannot replicate the work of God. But long story short, I grew up. And I'm currently a computer scientist. And that brings me to the main question for today. And the question is whether computer science is a real science. And there are several grounds to ask this question. And one of them, we can see just linguistically, we need to qualify science with computer science. We don't need for physics, we don't say physical science. We don't say biological science. These are real sciences. Social sciences, we have social science. Well, to make this example even more important, why we need this, how this qualifying works for the academics amongst us, we know that in assistant professor, assistant qualifies a professor, and then an assistant professor is not a real professor. Same goes for associate professor. The professor, we have the associate qualifies as professor, and the associate professor is not a real professor. The only unqualified professor is a real professor. And that's the reason that they need so many PhD students and postdocs, because otherwise they wouldn't be able to do their work. But other than linguistics, there is a more important issue that questions whether computer science is a real science. And if we look at the object of investigation, frog is an animal, and we actually don't know the provenance, so we believe it evolved over time, but there's no provenance for that. Computers, on the other hand, we have provenance. We know that they are the product of an intelligent design process. So that's the question, is whether computer science is a real science, or maybe it's just intelligent design. So to try to answer the question, I'll first give an example of some result in science. It's a result that it's mine because I have the opportunity to promote my results, and it's quite old. So it's actually it's I think that it is a fundamental result here that affects the whole field, and it's relevant to the conference, because many of the things that we will be discussed in the conference build on that or are similar to the same result. So it is important to start with something simple that people might know, hopefully know. And the way I present it, usually I start with, so we do a case study of hardware security, and the whole problem with hardware security starts with the fact that we have hardware, and this hardware costs a lot of money. So we want to have better use of our hardware, and what we do is the standard thing, we share. And when we share, we start getting into some problems. And to show these problems, the example that I usually give when I present all microarchitectural tasks to students is give the students a sample program, and I ask students to tell me what the program does. And invariably, students tell me that this calculates the hypotenuse of a square triangle. I never heard a different answer. I hope never to hear a different answer. But then I ask, what is the first thing that this program does? And for that, I get some variations, but all the answers are along the lines, it first multiply base by base, or if the students know a bit more, then they say it first allocates space for a variable base SQR, and then it brings base for memory, or something like that. And these are all interesting answers, but they are not necessarily correct. And the reason that they are not necessarily correct is that what we have here is an abstraction. We have code in a high-level language like C, and this code tells us what we want to achieve. And then we take this code and put it into a compiler, and the job of this compiler is not to follow the instructions that we are doing, that we are providing to it. The job of this compiler is to give us the result that these instructions compute. And if the compiler thinks that it knows what base is, it will not multiply, it will not create the instruction that calculates base times base. It will just square it and use that result. And if it knows that the base is 3 and the height is 4, it will just insert 5 into hypotenuse, and that's it. We will not have all these instructions. But even if we go into the machine code, it turns out that this machine code, if we have the machine code that implements this set of instructions, this machine code is still an abstraction. And the processor does not have to, and usually does not, follow the instructions the way we write them. It does whatever it wants, as long as it gives us, from our perspective, it looks like it has done this. So, and all the part that implements that, we call it microarchitecture. And now the question to us is, why are students not aware of that? And it's not only students, it's most programmers, and it's most computer scientists, and most everyone is not really aware of this issue. And the reason that the people are not aware is, again, computer science education, we are at fault. When students come to computer science lecture, we first tell them that this is how computers work. We have the von Neumann architecture, we have a control unit, reads the instructions from memory, execute the instructions, writes the results. then reads the next instruction, executes it, writes the result, and so on. And then we go to second year and we learn about architecture. If we are in good school, we see some more complex diagrams. Thanks, Daniel, for this one. And we learn that there is some real complex world underneath. If we are lucky, if we are not lucky, we still stay with the von Neumann architecture, just slightly more refined. And we continue our computer science education, and we learn high-level programs. And we focus on asymptotic behavior rather than real performance, because that's what we teach in computer science. And architecture is just a minor topic in what we teach. We finished that in second year. Hardly anyone goes further than that on looking at the hardware. And there is the important thing in computer science, which is the focus on abstraction. And this focus on abstraction is extremely important because we cannot really explain everything that goes at the minute details. So if we look at this presentation, we have about 1 million pixels here. Each of them has 24 bits of information for color. This is transmitted over an international, transcontinental line and reaches everywhere, everywhere in the world. We cannot talk about this in the level of bits and how they are moving around. So we need abstractions. And finally, the last element that we have is CPU vendors' interest that try to prevent us from knowing what really happens in the processor. And there are several reasons for that. And the good reason that they try to do that is that if we have a strict boundary, if we have the ISA interface, and that's the only thing that the vendors commit to, then they can change the processor independently of us changing the program, and everything continues to work. So it gives us an upgrade path that is really nice, and we're just decoupled. The other side that, or the other reason that vendors want to hide this information is that it contains some of their trade secrets, and they don't want all their competitors to know all the cool things that they are doing in their processor. But what this creates is that instead of working with a processor, instead of thinking about a processor, we think about an abstract thing, a von Neumann machine. And we have a gap between abstraction layers. And whenever we have gaps in abstraction, we have security issues. And one of the security issues that we have is with memory. And for that, here's an example. My first computer, you already know how old I am, so you can calculate the year it came out. This is an Apple IIe. It had a fast processor of 1 megahertz. It could do 1 million additions per second, which is way faster than what I can do. A recent machine that I bought had 20 hyperthreads. Each of them run at almost 4 gigahertz. So we opened about 5 orders of magnitude in speed. Memory also became faster. So my Apple IIe had the memory latency of 500 nanoseconds. Current memory has a latency of about 50 nanoseconds, so we improved by about an order of magnitude. Now, there are other improvements there, but we have not covered 5 orders of magnitude of difference, so we have a speed gap between processor and memory. And we need to bridge this gap. And the reason that we need to bridge this gap is that if we run a program, it takes time for the data to come to the processor. And running it again, or accessing it again, it will take a long time. And programs need to access data again. We have a locality in programs that means that we tend to access a similar location at the same time. So to bridge the gap, designers put a cache, which is a small bank of memory between the main memory and processor. And now what happens is that when we access memory, it is brought into the cache. And the next time we access it, we get it from the cache and we get fast access. Now, this is nice. It solved this speed gap problem, but it creates a different problem. And the different problem is that memory can change without changing the contents of the cache. And if we get data, then we get stale data. And This doesn't happen now, but it used to happen. And to solve this, we have an instruction, CLFlush, that flushes the contents of memory from the caches. And after that, we can access, will take us some more time, and we get the fresh data from the cache. This brings us to, so we have the behavior, we have timing difference between access and no access, and now we need to exploit this. And we have the Flush+Reload attack, which exploit this. We have a spy and the victim, and what the spy does is flush a memory line from the cache, wait some time, and in retrospect, we know that we need to wait because if we don't wait, the attack doesn't work, and I'll get to that a bit later. And while it waits, and after it waits, it measures how long it takes to read the data from again. And because we evicted it from the cache, this will take a long time. But if we flush it, wait, and during the wait, the victim reads the or accesses this location, then the next other attacker's access will be fast, and we know whether the victim has accessed the data. And we repeat this process, and we get an attack. We can find out what the victim has done, and we can the original attack showed how we break RSA from that with that, and from there it exploded to a large number of attacks that are based on Flush+Reload or use Flush+Reload in some sense. Now, the important thing from the perspective, we have the attack, but the more important thing to assess whether this is science or not is looking at the process of arriving to that. So I'll tell you now, it's a bit of a story, it's somewhat related. And it starts when I finished my PhD or was about to finish my PhD. We were contracted by the defense industry in Australia, and they had the problem with their calling submarines. And submarines they have a lot of control rooms. They have a lot of computers there. And a lot of computers weigh a lot, and they draw too much energy. And they wanted to reduce the footprint of these computers, because if we can put if we can put more fuel, we can increase the range just by reducing the amount of computers that we have on the submarine. And the solution they were looking at is virtualization. It's standard solution now as well. The idea is that we run multiple virtual machines on the same hardware. We have a hypervisor that isolates these and runs the information and ensures that each of them looks like an isolated machine. Now, this is it's easy to know that, yes, we can use that to save hardware, but the issue is that submarines the data that submarines handle is sensitive, considered top secret. So the question that they had is whether this solution is secure. And to assess that, they did what armies or defense do everywhere in the world. They hired the scientists to do the assessment for them, or to give them some information on the process, in the issue. And I happened to, after money changed a lot of hands, I happened to be the postdoc who was tasked with that. And I did the standard process of literature review and saying VMware hypervisor where that many bugs over the last years versus KVM that has less or more. I don't remember the details. But in addition to the review, they also wanted some experimentation, and they wanted to see if we can find something new. And things that I looked at, while I looked at the variables or the configuration, was transparent page sharing. This is a nice feature that the hypervisor have. It's less used today, but it was used a lot in the past. And the idea is that to save space, hypervisor shares pages from identical copy with an identical context. And the example here, we have multiple virtual machines. If we have identical content, we can keep one copy of that and give all other virtual machines access to the same content. And this works nice as long as no one changes the contents. So to solve changing the content, they use technology called copy and write, which makes sure that that the page is marked as read-only. If the virtual machine tries to change it, the hypervisor kicks in, copies the page, and gives the VM its own copy. And that means that writes to share pages are much slower. And I thought that I found a new attack there. And I came up with the hypothesis that I can exploit these time differences to detect what the software version running on each VM without actual accessing the VM. And following the usual process, designed an experiment, confirmed the hypothesis. I wanted to publish this publish a paper about that, read the literature, and find out that it has been known for at least 3 years there. So that sucks. We don't have a paper, but we are paid not to publish paper. We are paid to give a report. So in the report to defense, I told them, here we have that, and they asked me the important question: is this serious? And the answer is always, security. We don't say you have nothing to worry about, but just between us, being able to know what version of software runs on another VM in a submarine is probably not a major security risk. But then it occurred to me that when the physical pages are shared, we have the caching status shared between virtual machines. And this led to the hypothesis that we can determine what happens in other what runs in other virtual machines. And the result was Flush+Reload attack. So looking at that again, as computer science is real science, the answer is yes, we followed the same scientific process. We come up with an hypothesis, and this is true for almost every discovery that we see now. People come up with an hypothesis, come up with an experiment that confirms or falsifies this hypothesis, and then continues. And many experiments do not work, so sometimes we do not confirm the hypothesis. Moreover, it's very similar to what Galvani did, because basically what we're doing is we're taking some signal to an object that we don't really know how it works. In our case, it's a processor. In Galvani's case, it's a frog, but we give them some signal and learn from the response, we learn what they do. But there is still a difference. For our processors, we have a holy book that tells us what's inside. So the parts that we know of, we know some information, and the CPU vendors know even more. Yet, we only know part, and from discussions with CPU vendors or with representative CPU vendors, I'm fairly certain that even though they have the full design of the processor, they are not completely aware of the implications. Not because they are not intelligent. It is intelligent design. It's because these bloody things are extremely complex. With 10 billions of transistors, it's relatively hard to understand everything that happens. So, conclusion is computer science is a science, and important things: Luigi Galvani is cool, frogs are cute, sharing is risky, and for everyone, I do recommend continue reading the holy book, continue breaking stuff. It's fun, it's interesting. Enjoy it, enjoy the conference. Thank you, everyone, and I'll be happy to take questions.